So, in Unit 3 Miscellaneous, we're going to focus on some of the topics at the back end of Unit 3 that we will definitely cover pretty substantially in a few labs, at least one or two, but are not a huge part of the reading in the book. And so we kind of have to address them separately from any chapter. And so this is the Beer-Lambert law, and then separations of solutions and mixtures. So the Beer-Lambert law, also called Beer's law, is a relationship between the attenuation of light through a substance and the properties of that substance. That's a fancy, I don't even know, a synonym for attenuation. Basically, all it's saying is how much of the light gets through the substance. Transmittance is the fraction of incident light which is transmitted. In other words, it's the amount of light that successfully passes through the substance and comes out the other side. So what's transmitted gets there. If you transmit someone a message, that means you sent them the message. So transmittance is the amount of the light that gets from one side to the other. Absorbance is the flip side of it, of transmittance, and is how much is absorbed, how much didn't get through. So this is what it looks like. We'll use a machine to measure the absorbance of light depending on the chemical and the concentration of it. And so this is the incident light, the light shined on, and transmitted light is the amount of light that gets through. What doesn't get through is absorbed. Of course, the length of the container really matters because the longer you make this length, the more light gets absorbed and the less light gets transmitted. And so by measuring the starting light and the ending light, you can calculate what this chemical might be if it's unknown, or more likely, the molar concentration of the chemical in there by how much light it's absorbing. So the transmittance T of the solution is defined as the ratio of the transmitted intensity I, over the incident intensity IO, and takes the value between 0 and 1. So incident is the starting light, and then this is how much got through. So if none got through, then transmittance would be 0. If all got through, transmittance would be 1. However, it's more commonly expressed as a percentage. And so you might see something like this. So transmittance percentage just tells you what percent of the light got through the sample. The absorbance A of the solution is related to the transmittance and incident, and sorry, there's a typo there. It's related to the transmittance through the following equation. And so you can see that there's an inverse relationship. Now there's a logarithm in there that makes it a little more complicated, but still effectively, if transmittance goes up, that means absorbance goes down, and vice versa. I don't think AP Chem would ask you to calculate absorbance or transmittance, because they would have expected you to have done that in a lab and allow probably a formula used on Excel or something in order to do that. However, there is another formula which you will be expected to use, probably, but you should understand what transmittance and absorbance mean, and you should understand the relationship for sure. And so you can see, as absorbance goes up, transmittance goes down, and vice versa. So here's some visual examples of that. As the absorbance is higher, that means less of the light is getting through. What does that tell us? That tells us that the solution is more concentrated, and so less light is getting through. Besides the nature of the chemical itself, which is absorbing the light, there are two other factors which would dramatically impact how much light passes through. What would the relationship between the container, the length of the container, and the amount of absorbance that occurs? What would that relationship be? Pause the video if you need to. Okay, you should say that absorbance will go up as the length of the container goes up. And so we need to account for that, because if we don't, then the length of the container means that we'll get the wrong concentration values if our container is a different length than somebody else uses. So more absorbance or less transmittance as it gets longer, as the light is passing through more liquid, which increases the chance that it gets absorbed at any one point. What would be the relationship between the concentration of the chemical in the solution and the amount of absorbance that occurs? Pause the video if you need to, think about it. Okay, hopefully you answered. If you didn't answer, you should say, as the concentration goes up, the absorbance will go up, the transmittance will go down. Again, because there's more chance the light hits the chemicals in the solution. So the more concentrated the chemical, the more absorbance, less transmittance that occurs. So given the mathematical relationships I presented, the formula that's on your formula sheet that you need to be familiar with makes a lot of sense. And here it is. Absorbance equals the molar absorption coefficient. It's funny. I even forget that they use this symbol for this. When I see this symbol, I think of Twi and Ga, two languages from Ghana, because they use that E symbol, and I know a lot of other African languages do too, but I wonder, maybe they just thought it was a cool E. Who knows? Maybe somebody, anyways, that would be too much of a tangent, but makes me think of languages from my wife's country. But absorbance is A. The molar absorbance coefficient is E. Or if you were in Ghana, and then the molar concentration is C, and the optical path length is L. And so we can see we have absorbance here. If this is going to be specific for each chemical. So some chemicals, just at the same concentration, absorb more light, and some absorb less light. And then molar concentration, if it's higher, that means there's going to be more absorbance. And length of the tube thing. If the length of the tube is higher, that means more absorbance. And so hopefully based on what I explained in the previous slides, this makes sense. Notice that it is molar and it's per centimeter. I don't think, unless I missed it, I don't think that they actually have the units of this formula on your sheet. So I assume they won't try to trick you, and they'll give you the correct units and wouldn't ask you to unit convert. I don't know. That being said, units are molar and centimeters for this one. Every chemical has a certain wavelength at which its absorbance should be measured. So different chemicals absorb at different wavelengths. This is very important to make sure you're actually measuring how much light it absorbs by looking at its peak absorbance on a curve. This is also a way that you could identify what chemical there is in the liquid, because different liquids have different absorbances. So again, every chemical has a certain wavelength at which its absorbance should be measured. So for example, for this chemical, you should be measuring it around here, which looks like 555 or something like that, if I'm looking at this graph correctly. And this can be referred to as an absorbance peak. So actually measuring at the absorbance peak for a particular chemical is really important, because if we measure down here, we won't notice much of a change between these different concentrations. But if we are over here, then we can actually get more accurate measurements using peak absorbance, because we'll see a bigger difference in the absorbance values depending on the concentration. So it's easier to actually make an accurate measurement. And so it's very important. So using this equation, the Beer-Lambert law, a solution of unknown concentration can be calculated by comparing it to samples of known concentration. And so we can make, and we'll do this in a lab, God willing, we will make concentration versus absorbance line for a particular chemical. And then, if you have an unknown of an unknown concentration, well, what do? You find its absorbance, and let's say the absorbance is here. Well, then you can be like, oh, Buddha bada bing, that means the concentration is about 0.7 in this case. Okay? So that's the idea. We'll probably work with standard molar, though. I don't think we will be working with micromolar, but you never know. And if you forget what those units mean, hey, they were so generous, they put them right on the formula sheet for you there, at the very top. They didn't used to do that. They got very nice. They got very nice recently. So Beer-Lambert law additional notes. Remember or notice when we do the lab, or labs, that measuring absorbance must be calibrated. So if you forgot to calibrate, it's going to mess things up. It's an important way to account for the water itself. So if you didn't calibrate the instrument and account for the absorbance of water itself, then maybe, for example, your absorbances might be too high because the glass is naturally going to, like, even if you had pure water, transmittance isn't necessarily going to be 100% because maybe the glass is scattering something, maybe the water's scattering something, maybe there's some smudges on your glass or something like that. And so calibrating takes an account of that and says, okay, this is how much light gets through with nothing other than water in there. And then you add the chemical to say, and this is how much additional light the chemical is taking away to get actually good calibrated absorbance values. What sort of errors would increase or decrease absorbance? So for example, if the glass was smeared, absorbance would increase and the calculated concentration would be too high. And I said if you didn't calibrate, maybe the concentration would be calculated too high because your absorbance would be maybe higher because you're not accounting for like the water because you didn't calibrate properly. Just be aware that you could get questions along that sort, like, oh, Fanny Smith found that her absorbance was too high, explain blah, 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 blah. You've seen questions like that based on other types of labs, and that's something that's definitely in bounds for them to ask you. Okay, let's stop here and make a separate one next time for chromatography.